One more thing we have to talk about. So far, all of our cell potentials have been under standard conditions where we're using E naught, all right? However, in the Nernst equation, you can deal with cell potentials that haven't been studied under standard conditions. And if you're going to Death Valley or if you're going to the North Pole, you may not have 25 degrees Celsius. You might have different pressures, concentrations, stuff like that. So Nernst of the Nernst equation was the one that pulled this all together. And this thing right here is the Nernst equation. E, the cell potential under non-standard conditions, equals E naught, the cell potential under standard conditions, minus RT over NF natural log of Q. Oh, goodness, there's a lot of things right here. Anyway, R is the gas constant R, the energy R, 8.3145 joules per mole Kelvin. T is, big surprise, the Kelvin temperature. F is the Faraday constant. E naught, again, standard cell potential. All right, so you still need to figure out the standard cell potential. We're going to compare it with this other stuff to find the non-standard cell potential. N is the moles of electrons transferred. And then Q, as we'll see here in a little bit, that's the reaction quotient we saw back in chapter 13. It's like a non-standard way to calculate an equilibrium constant. And if that doesn't make a lot of sense, don't worry, I'll show you an example here in a little bit. Anyway, cell potentials under non-standard conditions, you really do need this Nernst equation because you can have a temperature other than 298 Kelvin. You can have different kinds of concentrations, which is where the reaction quotient comes in. So it can be a really helpful equation. It's kind of an ugly equation to use, but it does have a lot of really cool uses.
A zinc-copper cell shows a potential equal to the standard potential of 1.10 volts when both zinc and copper are in solution at the same concentration. If more copper ion is added to the cathode compartment solution, however, the cell potential increases.
So this is an example of where Nernst equation can be helpful. Okay, copper 2 plus zinc, making zinc 2 plus, and copper metal, which we've seen a lot of times. And we saw earlier that the standard cell potential, 1.10 volts. But that's assuming you're at 25 degrees Celsius and the concentration of the zinc 2 plus and the copper 2 plus ions, 1 mole per liter. Well, all of a sudden, you add some extra copper 2 plus, so it's no longer 1.0 moles per liter. Maybe it's 1.1. And if you look there carefully, the cell potential went from 1.10 volts to 1.11 volts. It went up. Now, if you go back to Le Chatelier's principle, if you add a reactant, the reaction will shift to the product side, all right? So that's Le Chatelier's principle, in effect, and that's totally cool. We can use the Nernst equation to actually calculate what the new potential is going to be. Obviously, adding the copper 2 plus made the reaction more spontaneous, like you had more action. E naught became more positive. Delta G equals minus NFE. You could figure out what the new delta G was. Anyway, Nernst equation will allow us to make sense of how this all works out. Let's do an example with the Nernst equation. Let's find the cell potential E, and there's no zero up there. Let's find the cell potential under these non-standard conditions when the zinc 2 plus is 0.0010 moles per liter, the pressure of the H2 is 0.10 atmospheres, and the pH is 0 at 290 Kelvin. And at first, when you look at that, you might be thinking, what the? Okay, and I totally dig it. So let's break this down. Let's figure out what the reaction is under standard conditions first, and we'll try to interpret all this. So you can see we have H2, we have some acid, H+, because that's what pH is all about, and we've also got some zinc 2+. So if you think about this long enough, this is nothing more than the zinc reaction reacting with the She electrode. And we saw earlier that this has a standard cell potential of 0.76 volts. She is automatically 0, and from She you can figure out that zinc going to zinc 2 plus is 0.76 volts when written as an oxidation. So the E naught, the standard cell conditions, if this was 298 Kelvin and all the atmospheres were 1 and the concentrations were 1 mole per liter, the cell potential would be positive 0.76 volts. However, in this example, we're going to see we're not under standard conditions. So we're going to take this 0.76 number and do some stuff to it. Now, along the way, before we go, I want you to see that the N, the number of electrons transferred, it's 2. The zinc gave up 2 electrons and the She electrode gained 2 electrons. So the N value is literally the number of electrons that are taken or transferred in a redox reaction. The Nernst equation, E equals E naught minus RT-NF natural log of Q. Okay, no problem. Let's deal with the RT-NF and E naught parts, and we'll do Q here in a little bit. Now, the cell potential under standard conditions, that's the 0.76 number. Then minus RT-NF minus R minus T in Kelvin. N is 2, F is 96,485. All right, so that's the E naught minus RT over NF part. But then we've got natural log of Q. Now remember, reaction quotients Q, products over reactants, and everything raised to the power, don't include solids, etc., etc. Now, in this problem, this is what we want to use for Q. So we're going to have zinc 2 plus and H2 gas in the product side, the numerator, and we'll have H plus squared in the denominator. And we're going to put in the different values. So here's the zinc 2 plus, here's the pressure of the H2 gas. We need to figure out what pH of 0 means, etc., etc. Well, pH is easy. You can turn that into H plus by going 10 raised to the power of minus pH. So that's actually 1.0 moles per liter. That is actually a standard condition for these kind of problems. So the Q then, products over reactants, zinc 2 plus times the pressure of hydrogen divided by H plus squared. This is what they call a mixed equilibrium constant because you have pressures and concentrations, and that's okay for these kind. Anyway, 0.0010, that's the zinc. Here's the pressure of the hydrogen gas. 1.0 moles per liter is the H plus concentration. You can solve for Q this way. If you do all this right, you go minus RT over NF and then natural log of all this stuff right here, you should get for all of that positive 0.12 volts. So the E potential, the cell potential of our non-standard conditions, 0.88 volts. Whoa. Okay. Why this is more positive than the standard condition is because our zinc 2 plus and hydrogen gas are less than standard. Like zinc 2 plus standard would be 1 mole per liter and it's 0.0010. And the pressure of H2 normally would be 1 atmosphere and this is 0.1 atmospheres. So what that means here, we've essentially lowered the product concentrations. And by Le Chatelier's principle again, you take out a product, the reaction should shift to the side you take something out from. That's going to shift this to the right. More to the right means more spontaneous, which means bigger E. So Nernst equation fits in really well with everything else we've done. And I kind of like this problem. It's kind of towards the end of Chem 223. We've got the pH, we've got the cell potential, we have Le Chatelier's, we've got redox, we've got energy R. I mean, we even got the Faraday, right? We've got everything in here in this Nernst equation. Anyway, it's towards the end of the term. I got to chill out here. But anyway, hopefully you see the utility of it. If you have one of these weird conditions and stuff, you can actually figure out how this stuff works out. There are quicker ways sometimes to calculate these combinations. You can go directly from a cell potential to an equilibrium constant if you want, using E naught equals RT over NF natural log of K. And sometimes people use this. I usually am a person, I go through delta G. So if I had an E naught I wanted to turn into K, I would first go delta G equals minus NFE. And you have to remember delta G is also equal to minus RT natural log of K. And if you combine both of those, that's where this equation pops into. If you're at 298 Kelvin, and remembering that R is a constant and also the Faraday, E naught equals 0.0257 divided by N times the natural log of K. So that's another way that kind of helps out and stuff here. N, of course, is all over the place, depends on moles of electrons transferred, but if you're at 298 Kelvin, which is really common, then you can substitute in 298 times R divided by F to get that constant, and you're good to go. This is a triangle that sometimes people use in this material. It just shows the different ways to go between delta G, E, and K. So I talked about earlier how delta G equals minus RT natural log of K. That goes on the left-hand side of the triangle. On the bottom, delta G equals minus NFE. And on the right, then you have this E cell equals RT over NF natural log of K. Oh, the places we will go.